Hello everyone, and thank you for joining us online today. My name is Ionela Mocanu, and I will present you today an approach of integrating pack semantics with SMT solvers. This approach is the first of its kind and proposes an algorithm that decides entailment of SMT formulas while learning new constraints implicitly. By implicit learning, we mean the kind of learning where the algorithm doesn't produce an explicit representation of the hypothesis. The algorithm, called the SciPack, uses both knowledge base and a finite set of examples in order to decide entailment of the query. We augmented this framework to the arithmetic domain, allowing for continuous data values and reasoning with more expressive languages. We will now present a small example to see how it works. Consider a smart house system which maintains the temperature and ventilation of the rooms at the optimal conditions. The interactive system is capable of answering queries such as whether a particular room is sufficiently ventilated or not. The system is characterized by the following parameters: T representing the temperature in the room, the amount of carbon monoxide detected, the number of people present, and the ventilation score, which can be an integer between 1 and 5. All these variables are constrained within some ranges and can be represented as conjunction of constraints, all of them encoded as knowledge base of the system. Regularly, the system receives from the sensors new information about some of these parameters. For example, the sensors transmit updates at moments 1, 2, and 3. As we can see, some of the variables are not seen due to, let's say, faulty sensors or just missing data. Here, the sensors do not contain any information about the carbon monoxide in that room, but we do know from the knowledge base that the amount of carbon monoxide is within some range, less than 180. Consider the case where we ask the system the following question: whether the carbon monoxide per person is less than a value 60 in that room. Using the knowledge base alone is not sufficient to decide its entailment, but after receiving observations about the number of people in that room, we gain some additional knowledge. We know that there are at least 3 people in that moment. This forms our implicit constraint that the number of people is at least 3 resulted from the partial information received. Knowing that the number of people is greater or equal to 3 and that the carbon monoxide value is less than 180, we are able to decide that the query is entailed. This knowledge has been formulated implicitly by looking at the knowledge base and query with respect to the partial information. We reiterate that the knowledge base alone is not sufficient to decide whether the query holds. Moreover, the partial observations only give us information about some of the variables, and so it is not sufficient to infer the truth of the query. We require both the knowledge base and the partial assignment to establish that the query is entailed. This kind of knowledge was gained without explicitly trying to model it. We did that using the pack learning framework for logical formulas. Probably approximately correct, or pack learning, is a machine learning framework where the classifier receives a finite set of examples, x1, x2, x3, xn, drawn from a distribution where xt is a target attribute. The classifier has to return a generalization function for those examples within a class of possible functions. Pack learning guarantees that given the free parameters epsilon and delta, there is an algorithm that outputs with probability greater than 1 minus delta a hypothesis function f that has a generalization error less than epsilon. The main property of this approach is that for the classifier to be approximately correct, it needs at least m sample points, where the value m can be precomputed. Later on, Leslie Valiant formulated this pack learning for the logic, which became the pack semantics. In contrast to the pack learning, the pack semantics returns an approximate validity of a given formula with 1 minus delta confidence. This was a brief introduction about the pack. Now we'll talk about the SMT component. Recall that SAT is the problem of deciding satisfiability for Boolean formulas, whereas SMT decides satisfiability for more expressive domains, which require some background knowledge. A formula is satisfiable if there is an assignment of values that give that formula the value true under evaluation. The first work on this side pack has been proposed by Brandon Juba on propositional logic, followed by an augmentation of this framework to first-order logic. Our work extends these previous results to a more expressive language domain, the arithmetic domain, which is widely used in artificial intelligence to represent complex problems and more specifically in the context of knowledge acquisition. This extension allows for continuous ranges of values and intervals, overcoming some of the limitations of the previously proposed domains. To decide set of arithmetic formulas, we use off-the-shelf SMT solvers. To maintain the polynomial guarantee, we select those fragments for which there is a polynomial-time decision procedure. For example, in the fragment of difference logic, we use the Bellman-Ford algorithm. These were a few words about how we use SMT solvers in our approach. We will now introduce the masking process. Let's consider a Boolean formula alpha, A or B, and B or C, for which we have a full assignment of values, capital R, and a partial assignment, which covers some of the values of the assignment and replaces them with the symbol star. When we evaluate the formula with respect to the full assignment, we obtain a value true or false. In this case, we obtain true. But when we evaluate the same formula with respect to the partial assignment, what we obtain is another formula called restricted formula, because not all attributes are known, in this case, the value for the variable d. We are training our algorithm on incomplete data in order to simulate the real-world scenario where the data points received might be corrupted or missing. We do this by applying a masking process on each assignment, which covers basically some of the attributes randomly. Not all SMT solvers successfully deal with this kind of restricted formulas, this property being called restriction clause property. In order to guarantee that our solvers do meet this property, we are going to integrate only sounding complete solvers, such as Bellman-Ford algorithm for difference logic. These were the main components of our algorithm. Now we will briefly explain how these fit together. As input, we have the pack-free parameters epsilon to set the error rate and delta for the confidence rate, the knowledge base, which is a set of constraints, the query we intend to decide, and a set of partial observations, where the masking process has been applied beforehand. Additionally, we plug into our algorithm the SMT solver corresponding to our language domain of interest. The algorithm returns accept if the query holds with at least 1 minus delta validity and reject otherwise. To sum up, we have covered so far the SMT learning and semantics, the use of SMT solvers, and the masking process, and we briefly introduced the main algorithm. Our paper is called Polynomial-time Implicit Learnability in SMT by the authors Ionela Mocanu and supervisors Vaishak Bell and Brandon Juba. Thank you very much for listening this far, and if you have any questions, I'm happy to answer.